Today's lecture will be about the analysis of clocked sequential circuits. And the outline of this presentation is as follows. I'm going to talk about the state equations, the output equations when we do the analysis. We look at the meaning of a state table and state diagram. So really the purpose of the analysis is to come up with so given a sequential circuit, if we have the diagram, then you can analyze it. And the purpose of this analysis is to come up with a state table and state diagram, okay, for the sequential circuit. In this presentation, I also have the topic about Mealy versus Moore sequential circuits. So there is a small difference between these two sequential circuits. We're going to study them in great details. We're going to look at their state diagrams and their timing diagrams, and look at the differences between these two different sequential circuits. Right. So the meaning of analysis. Okay, so when we analyze a circuit, we are describing, okay, what the circuit does. Okay, that's the meaning of analysis. We try to understand and describe what the circuit does. The way that we do it is that we look at the equations. Okay, so we can describe here the output based on the inputs and the state of the flip-flops. So in the case of sequential circuit, the output depends not only on the inputs, but also it depends on the present state of the flip-flops. So for this reason, we need to determine, okay, we need to look at the state of the flip-flops and determine the equations and so we need to fill the state table and draw the state diagram. So the analysis procedure is simple. So we have 4 steps. Step number 1, obtain the equations at the inputs of the flip-flops. That's step number 1. Step number 2 is to obtain the output equations. Then step number 3 is to fill the state table for all the possible inputs and state values. And step number 4 is to draw the state diagram. If we have done these 4, then we are done with the analysis. So these are the 4 steps in the analysis procedure. Here's an example. Right. The first thing you need to look at is that whether this is a combinational circuit or a sequential circuit. So the question is this a sequential circuit? Students, please answer me quickly because we don't really have that time. Is this a sequential circuit? I really need someone to answer. You can actually, all of you can answer. Yes, why?
It has the clock. That's the first thing I noticed.
Yes, what else? We have these D flip-flops, right?
Yes.
So the D flip-flops are memory elements, and because we have memory elements inside the circuit, then this makes it a sequential circuit. So remember, a sequential circuit, it has flip-flops. Okay, so that's what makes it sequential. And the clock here, it means that these flip-flops are synchronized with the clock, so we call it a clocked sequential circuit or synchronous sequential circuit. So the answer is yes. Right. What type of memory? What type? Come on, you have to answer these questions. What type of memory do we have here? No answer? Nobody would like to answer? D flip-flops. Is that too difficult, Yani? D flip-flops. We have D flip-flops. We are using D-type flip-flops inside the sequential circuit. So notice the D input here. These are the simplest flip-flops that you can have in a sequential circuit. D flip-flops. Okay, so remember that the flip-flops, they are called the flip-flops because they are sensitive to the edge of the clock. Notice the clock input here. This arrowhead indicating that these are flip-flops. Fine. The next question, how many state variables? The meaning of state variables here, it means that how many flip-flops do you have? We have 2, right?
2, yeah.
Yes. Now, the meaning here of the state appears at the output of these flip-flops. So notice that the output here is A and B. These are the outputs of the flip-flops. So these define the state variables. So we have two state variables, A and B. So remember that what you are storing inside the flip-flop appears as its output. So the output of the flip-flop, it means that this is the state variable. So we have two flip-flops, so we have two state variables. What are the inputs? Can you see my slide? X, exactly, X inputs. What are the outputs?
Y.
A and B.
Y.
Yeah, Y. Now you can actually see that also A and B, these are actually state variables, and sometimes we use the state variables also as outputs. But really in this circuit, we only have one output, Y. But sometimes we can use the output of a flip-flop as also the output of a sequential circuit. That also is possible. Right, so now we have seen, okay, so this is the first thing that you need to actually answer. So you have to answer these questions. And then you can say, okay, what are the equations at the D inputs of the flip-flops? So what is the equation for DA and what is the equation for DB? Now these are easy, right? Because we are describing them with this logic. So what is this logic? What is DA? So here you have A, this is X. Here you have what? X, and this is what? This is B, right? So you can write the equation for DA as AX or BX. How about the equation for DB? This is X.
A prime and X.
Thank you very much. Okay, so it's A prime and X. So now we have obtained the equations at the inputs of the flip-flops. Now, what does it mean to have equations at the inputs of the flip-flops? What's the meaning of DA and DB in the case of a D-type flip-flops?
Set.
Well, yes, but these are called the next state equations. So the A and B, these are the outputs. These define the current state or the present state. Okay, so this is the state now at time equal to t. So I can write A at time equal to t is simply the output A, and B at time equal to t is simply equal to B. So it means here t, it means now during this clock cycle. Whereas the next state, this will be A at t plus 1 and B at t plus 1. So this will happen after the rising edge of the clock. Okay, so the flip-flops are synchronized with the clock, and therefore they will change their output at the next rising edge of the clock. So A at t plus 1 becomes DA, which is the input, and B at t plus 1 becomes DB. So this is why we say that DA and DB, which are the inputs to the flip-flops, are defined in next state. This is very important. Okay, so the next state appears at the inputs of the flip-flops, and the current state appears at the output. Okay. Oh, this is the meaning here of, so the values here of A and B will be DA and DB at the next clock edge. So basically, we're going to change A and B cycle by cycle. We change it at the rising edge of the clock. So these are the flip-flop input equations. Yes, Fadal.
What does it mean by t plus 1?
It means next cycle. Because t means now. T plus 1 means next cycle.
Okay.
So if t is now, then t plus 1 will be after the rising edge. So the rising edge of the clock will define the beginning of the next cycle. See that here time is very important because we are using a clock, and time is very important in the case of sequential circuits. So these memory elements are synchronized with the clock, and this means that we are going to change, okay, their state or the outputs of these flip-flops cycle by cycle. We are going to change A and B, and the value of A at t plus 1 and B at t plus 1 will be dA and dB. So now we can say, okay, so now we understand this. So we define here the next state, as I said, okay, that A at t plus 1 is nothing but dA is given by this equation, and dB, which is B at t plus 1, is nothing but dB is given by this equation. Okay, so these are the next state equations. We have obtained the next state equations, okay, for this sequential circuit. And there is only one output Y. We can obtain the output equation. So what is the output equation? We have this logic here for the output Y. Can you tell me what's the equation for Y? Can you see it? This is B, right? We are connecting B here, right? Back all the way here to this OR gate. We are connecting A. We are connecting it back here. And this is basically X. This is X prime. So it is A or B and X prime. That's basically it. That's my output Y. So this is the output equation. So the circuit diagram is given to us, and we obtain the equations. So we have the next state equations, and we have the output equation. What is next? What shall we do next? According to the analysis procedure. So we obtain the next state equations, we obtain the output equation. What is the third step? Draw the state
table.
Yeah, state table. So the state table is what? The state table is like the truth table. In the case of combinational circuits, we use truth tables. So the truth table, we place the input and we look at the output, and this is the truth table for the combinational circuit. In the case of sequential, we use a state table. So the meaning of state table is like the truth table, but it's for a sequential circuit. So in the case of state table, we place the input X, but this is not sufficient because the next state and the output depend also on the present state. Now the present state that appears, okay, here at the outputs A and B, this is the present state. We use it as input, okay, in the state table, because the next state and the output depends on the present state, not only the input X. So we have A and B. These are two state variables. We use them like inputs in the state table, and also we have the input X. So we have three things. We have A, we have B, we have X, and therefore we have 8 possible rows inside the state table. Notice that A, B can be 0, 0, it can be 0, 1, it can be 1, 0, and it can be 1, 1. So these are the 4 possible states based on the value of A and B. The input X can be 0 or 1. So in total, we have 8 possible combinations. So we have 8 rows inside the state table. So what we need to do is that we need to look at the next state. So the next state here is A at t plus 1 and B at t plus 1. So and the author calls this A star and B star. That's in your textbook. A star and B star, they mean the same thing. That will be A at t plus 1 and B at t plus 1. So this is A star here. And this is B star. Okay. And we just have to evaluate these two equations. So in the case of A star, okay, it is A and X or B and X. It depends on A, B, and X. So notice that if you have A and X is equal to 1 or B and X equal to 1, you get a 1. So notice that here we have B and X equal to 1. Here we have A and X equal to 1. So you get 1. Here you have A or B, actually both of them are equal to 1, and we have X equal to 1, you get a 1. So these are the ones that appear under A star. So this is basically the evaluation of this equation. So it depends on A, it depends on B, it depends on X. So you have to use the present state as if it was an input, okay, in the state table. In the case of B star, this is basically here. Okay, it's A prime and X. So A must be 0 and x equal to 1. So notice that here A equal to 0, x equal to 1, you get a 1. Okay. Similarly, here you have A equal to 0, x is equal to 1, you get a 1. Otherwise, it's actually everywhere is 0. So basically, you evaluate, okay, these equations, these expressions. You evaluate them and you place the value of A star and B star, and these are called the next state. This is the next state. You can also evaluate Y. Notice that Y also depends on A and B and X. So it's A or B and X prime. So A or B must be equal to 1 and X must be equal to 0. Okay, so let me just clean up this ink here. So notice that here Y is equal to 1. So here you have A or B is equal to 1 and X equal to 0. So that's actually X prime. Here is the same thing. You have X equal to 0. This is A or B. This is the same thing here. So you get the output Y is equal to 1. So notice that you obtain the next state and the output. They have to appear in the state table. Okay, that's the meaning of the state table. So we have 8 entries in total because we have the present state, you have 2 state variables, and you have the input X. So for this reason, we have 8 possible combinations, and we have 8 entries inside the state table. Now, the same state table, we can draw it differently. Okay, we can draw it. This is another form of the state table. Now, this will be useful. You can actually look at the present state, and you have 4 possible values of A and B. And you look at the next state. You look at the next state when X equal to 0 and when X equal to 1. Okay, so when X equal to 0, you have actually A star, B star equal to 0, 0. So basically, we can copy these entries here. And when A is equal to 1, sorry, when X equal to 1 here, we look at this, 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 and this. Okay, and we copy them here. So this is another form. It contains exactly the same information, but it's another way to draw the state table. The output Y, you can show the output Y when X equal to 0, and you can show the output Y when X is equal to 1. Again, you just actually copy the entries, this one, this one, this one, and this one. This is when X equal to 0, and you copy the other ones when X is equal to 1, when X equal to 1, yes. Right. So these are 2 different ways to draw the state table. Now, once you have the state table, the final step would be to draw the state diagram. And this can be drawn very easily. The state diagram is a graphical representation. It's a graphical representation of a state table. So the same information that exists in the state table, we can place it in the state diagram. Notice that here the present state, it can be. So we have here 2 state variables. So we have 4 possible states, 0, 0, 0, 1, 1, 0, and 1, 1. Now, the way that we draw the states, they appear as circles. So this is actually here state 0, 0. So this is AB equal to 0, 0. This is AB equal to 0, 1. This is AB equal to 1, 0. And this is AB equal to 1, 1. So we have 4 states, and these appear as 4 circles in the state diagram. So these actually are the states. What you need to do is that you need to define the transitions between the states. So the transitions are the arcs. The states are the circles, and the transitions, the state transitions here are the arcs. So you look at the next state. So the next state here will define the transitions between these states. So start at state 0, 0. Let us start here at state 0, 0. Now, if X equal to 0, then the next state will be 0, 0. So you can see that we have a transition, okay, from state 0, 0 back to itself. We have this transition, okay? Now, this is X. This is X equal to 0. And here we have slash Y. This is Y equal to 0. Notice that the output Y is equal to 0. Okay, when you are in state 0, 0 and the input X equal to 0, you get the output Y equal to 0. So the output Y is shown on the arc. Okay, it's shown on the arc in this example. If the input X is equal to 1, then you go from state 0, 0 to state 0, 1. So that's here state 0, 1, and you have this transition here. This is when X is equal to 1. So this is X, this is Y, this is slash Y, okay? So notice that Y is also equal to 0. So when X equal to 1. So the output here appears on the arc. If you are in state 0, 1, if you are here, and the input X equal to 0, then the next state will be 0, 0. So you have a transition from 0, 1 back to 0, 0. That's when X is equal to 0. The output Y will equal to 1. So this is slash Y. And if the input X is equal to 1, then the next state will be 1, 1. So this is X here equal to 1. The next state will be 1, 1. And the output will be 0. So notice that this is slash the output Y is 0. So this is the input X equal to 1. And then the output Y equal to 0. So the arcs indicate the state transition. So we get this information from the state table and we draw it in the state diagram. And we can complete the state diagram by showing all the state transitions between the states, depending, of course, on the input X. So we show the input X on the arc, and then we put slash, and then we show the output Y because the output depends on the input as well as the present state. So we get the output also from the state table and we place it on the state diagram. So both the state table and the state diagram show exactly the same information. Do you have any question about this? Is this clear, students? Right, this is very important. You really need to understand, okay, the meaning of the state table and the state diagram, okay? And remember that the states here, okay, mean the output of these flip-flops that exist in the circuit diagram. These define the states. We have 2 flip-flops, we have 2 state variables. This will give me 4 states because we have 4 possible combinations of A and B. The state transition indicates what will be the next state during next clock cycle. So we make a transition from one state to another state at the edge, at the rising edge of the clock. Now, the analysis, there is a small difference between the analysis of combinational circuit and sequential circuit. We have seen already the analysis of combinational circuit. That was very easy, very simple. So in the case of combinational circuits, we obtain the Boolean equations. These equations appear, okay, we get them at the output of the combinational circuit and we fill the truth table. All what we have to do is just fill the truth table and we are done. That's the analysis of combinational circuits. In the case of sequential circuits, the story is different. So in the case of combinational, the output is a function of the input only because there is no state. There is no memory inside the combinational circuit. In the case of sequential circuit, what we have to do is that we have to go these 4 steps, obtain the next state equations, output equations, fill the state table, and draw the state diagram. These are the 4 steps. So now we can say that the next state, okay, is a function of not only the input, but also the current state. So it depends on the input and the current state. The same thing can be said for the output. It's also a function of the input and the current state. So it's not only a function of the input, it's not combinational, it's sequential now. So it's a function of the input as well as the current state. So this is really the difference between the analysis of sequential circuits and combinational circuits. And this is slightly more difficult. Yeah, the analysis of sequential circuits. It's not really that difficult. You can do the analysis very easily, okay, given the circuit diagram. Right. Let me show you a second example. Okay, let me show you here a simple example. Notice that we have 2 inputs, X and Y. There is only one state variable, which is A. You can see there's only one D flip-flop. So the output of the flip-flop is the state variable. I'm calling it A, or you can call it a QA if you want. You can call the input DA. Okay. You just give them names. This is the input, okay, to the D flip-flop. Notice that the type of the flip-flop is D. It's a D type. That's what makes the analysis very easy. Okay, in the case of D flip-flops, It's so simple. There is no separate output. I can use the output of the flip-flop as the output of the circuit. So I can say the output is the current state A. Sometimes in some sequential circuits, you can take the output of the flip-flop and you can use it as the output of the sequential circuit. Now, what we need to do is we need to obtain the next state equation. We need to obtain the state table and the state diagram. Okay, so in order to do this analysis, I have to obtain the next state equation. The next state equation is very easy. Obtain the equation here for dA at the input of the flip-flop. Once we have this equation, we can fill the state table and we can draw the state diagram, and this should be very easy. So notice that we only have one flip-flop. This will give me only one state variable. So the equation is very simple. Okay, so we have here two XOR gates. So this dA, this is of course this is A. A here is nothing but the output of the D flip-flop. That's the present state. So it is A XOR X XOR Y. That's dA. Okay, that's the equation for dA. And this is what is the next state equation. So dA here is A at t plus 1, and sometimes I call it as A star. So this is basically dA, and this is given by this equation. So we have the next state equation. That's actually so simple, so easy. What we need to do is that we need to draw, okay, the state table and the state diagram. The state table, okay, is simple. What we have is that we have only one state variable A. We have two inputs X and Y. So in total, we have 3. So therefore, we have here 8 rows inside the state table. Okay, so A can be 0. A can be 1, and the value of X and Y, we can actually go from 0, 0 all the way to 1, 1. What we need to do is we need to determine the next state. So the next state, we call it A star or A at t plus 1. And this is nothing but dA, and it's given by this equation. So it is A XOR X XOR Y. So take the XOR here, okay, of 0 XOR 0 XOR 0 will give me 0. 0 XOR 0 XOR 1, this will give me 1. That's an odd function. You can see this is 1, this is 0 here because you have 2 1s. When you XOR 1 with 1, you get 0. And so on. So basically, this column here is nothing but this equation. So we're evaluating this equation, and this is my next state. So we have the state table. That actually was really easy to obtain. Now I really need to draw the state diagram. Let me ask you this question. How many states do we have in the state diagram? Very simple question.
2.
Yes, 2. What are these 2?
X and Y.
No,
A prime.
no, A equal to 0 and A equal to 1. Because the states that appear in the state diagram depend on this A here. So A can be 0, A can be 1. So we have these 2 states. Let me just erase this ink again, just to make it clear for you. So we have 2 states. A can be equal to 0 and A can be equal to 1. These are the 2 states. So I have to draw 2 states. Now we have 2 inputs, X and Y. Okay, so we have, depending, of course, on the input X and Y, we can draw the arcs. The arcs here is the transition from the present state to the next state. So in the state diagram, we only have 2 states. So that's A equal to 0. And this is A equal to 1 in the state diagram. This is actually very simple, very easy. I know that there are 2 states because there are only 2 possible values for the state variable A, 0 and 1. Now, in order to draw the arcs, so these are the circles, these are the states. In order to draw the arcs, which are the transitions between these 2 states, we look at all the possible inputs, X and Y. We have 2 inputs here, X and Y. So this is here XY. So when XY equal to 0, 0, we make a transition from 0 back to 0. You can see that this is actually my arc from 0 back to 0. The same thing here, when the input XY equal to 0, we make a transition from 0 back to itself. This is actually XY here equal to 1, 1. So either we have xy equal to 0, 0, or we have xy equal to 1, 1, and this will take me from state 0 back to itself. Now, if xy equal to 0, 1, notice that we are making a transition from 0 to 1. So you can see that here we have this transition. This is when the input here, xy equal to 0, 1. The same thing for 1, 0. The next state is also 1. So this is also xy. When it's 1, 0, we make a transition from state 0 to state 1. You see how easy? It's very simple. So we're actually taking the information that exists in the state table and we are copying it into the state diagram. But we are doing it graphically. So the state diagram is more like a graphical representation of the state table. Similarly, when we are in state 1, so here we are in state 1, look at all the possible transitions. So 0, 0 will take me from state 1 back to state 1. So it's this arc. That's actually when xy equal to 0, 0. The same thing here. 1, 1 will take me from state 1 back to itself. If the input is 0, 1 or 1, 0, then this will take me back to state 0. So you can see that here we have the transition, okay, from state 1 back to state 0 if the input xy is 0, 1 or 1, 0. So what is shown on the arc is the input. So we have two inputs here, x and y. So xy here can be 0, 1, or it could be 1, 0. So these are the inputs x and y. Okay, so I'm showing them with 2 bits. And the arcs indicate the transitions between these states. So there are only 2 states because there is only 1 state variable. So this flip-flop here, this D flip-flop can only store actually either a 0 or a 1. So for this reason, we only have 2 states inside. We only have 2 states in the state diagram. Okay, is this clear? Any question about this? I do have more examples. Let us move on. Let me show you a sequential circuit with a different type of a flip-flop. Notice that this flip-flop here is a T-type flip-flop. So notice that this is T. It means a toggle flip-flop. We have 2 flip-flops. Their outputs are called actually A and B. So these are my state variables. So what I really need to do is that I need to obtain the equations at the inputs of the flip-flops. So these are called the T flip-flop input equations. So I need to obtain TA and TB. And then once we have the equations for TA and TB, we can obtain the next state equations. Now, the next state equations are not the same as the input equations. In the case of D flip-flops that we have seen in the previous 2 examples, the next state equation is identical to the input equations. So basically, when I say A at T plus 1 or A star, it's DA and B star is DB. But in the case of T-type, the toggle flip-flop, this next state equation is not identical to the input equation. So there's a difference. So we have to obtain both the T flip-flop input equations and the next state equations. Once we have these equations, we can fill. Once we have the next state equations, we can fill the state table, and then we can draw the state diagram, and we are done. So let us do this. Well, in the case of the T flip-flop, okay, you have to recall the characteristic equation, because the characteristic equation will tell you what's the next state of the flip-flop. In the case of the D flip-flop, the characteristic equation was so simple. Q at T plus 1 is equal to the D input. So if you have the input equation, then that's the next state equation. So this is why the D flip-flop is so simple and so easy, and designers actually love the D flip-flop because it's actually so easy to deal with. In the case of a T-type flip-flop, notice that the characteristic equation is different. We are actually XORing the output Q with T to determine the next state. So the T input is XORed with the output Q to determine Q at T plus 1. So for example, if T equal to 0, you get Q at T plus 1 is equal to Q, and there is no change. And if T is equal to 1, when you XOR with 1, if this is equal to 1, you get Q prime. So we are inverting the output. So that's the T-type flip-flop. It is actually the toggle. It will invert okay, complement its output. We also have the JK flip-flop, but I'm not going to spend time on it. This is even more complex. So it has actually more complex equation as shown here. Already we have seen it in a previous lecture. So the focus now will be on the T flip-flop. So we're going to focus on this characteristic equation. We need it actually for the analysis of the sequential circuit when we have T flip-flops. So let us go back to the circuit diagram. So this is my circuit diagram with T flip-flops. This is my sequential circuit. So notice that we have the clock input here. It's connected to the clock of both flip-flops. Notice the arrowhead indicating that these are flip-flops. Notice the T input indicating the type of the flip-flop. There is also a reset. Now that's interesting, is that you can actually reset both flip-flops. Now this reset has a special reset input here, indicating that this reset is asynchronous. You can reset at any time, even without the edge of the clock. Notice that the reset input is inverted, indicating active low, not active high. So when the reset equal to 0, we are resetting. When reset equal to 1, then there is no reset. So this is important if you would like to reset these flip-flops initially before you start operating the circuit. Okay, sometimes you would like to reset before we start using the sequential circuit. Right. So now what we need to do is that we need to obtain the T flip-flop input equations. And this is easy. We need to obtain TA and TB. Notice that TB is nothing but X. In the case of TA, it is X ANDed with this B. So notice that this B here is connected back to this AND gate. So TA is actually B and X, and TB is equal to X. So these are the T flip-flop input equations. But this is not the next state. In order to obtain the next state, you have to go at the characteristic equation. So you have to XOR TA with A to obtain A at T plus 1. So the next state equations, A at T plus 1 and B at T plus 1, you have to XOR TA and TB with A and B respectively. You have to do that in order to obtain the next state equations, because this is not a D type, it's a T type. It's a toggle. So therefore, substitute TA and TB. Okay, then you get actually here BX XOR A. Here you get X XOR B. So these are the next state equations. So this is how we obtain the next state equations. If you have the next state equations, then it will be very easy to fill the state table and to draw the state diagram. Okay. There is one more thing here, which is the output Y. The output Y here is just simply the output equation is what? Y is equal to what? Can you tell me? It's very simple.
A and B.
A, B.
Exactly, A and B. So that's actually very easy. Notice that the output Y does not depend on the input X. This is something interesting, okay? It does not depend on the input X. It only depends on the state, the present state. So remember that A and B, which are the outputs of the flip-flops, define the present state. So that's an interesting sequential circuit. Now we have the equations. We have the next state equations. We have obtained the T flip-flop input equations. We have obtained the next state equations. We have the output equation. All what we have to do is to draw and fill, okay, this state table. So we have two state variables, A and B. So they define the present state. We have 4 possible combinations, 0, 0, 0, 1, 1, 0, and 1, 1. We have one input X, so it can be either 0 or 1. So this will give me 8 possible combinations in total. We have A star. This is the next state. We have B star. This is A at T plus 1, and this is B at T plus 1. That will be the next value of A and B after the rising edge of the clock. So use these equations. This is nothing but A star. This is the equation. And this is nothing but B star. This is the equation. So evaluate this equation, calculate B and X XOR A. This will give you actually A star, and evaluate X XOR B to get B star. Okay, so notice that here when you XOR 0 with 0, X with B, you get 0. When you XOR it with 1, you get 1. The same thing here, 1 XOR 0, you get 1. And 1 XOR 1, you get 0. So that's basically how we obtain B star. All what we have to do is evaluate this equation. You can do the same thing with A star by evaluating this equation. And the output Y is simply A and B. So basically, when both A and B are both 1 and 1, you get the output Y equal to 1. And it does not depend on X. It only depends on A and B. Now we have the state table. All what we need to do is from the state table, draw the state diagram. While the state diagram here is simple to draw because we only have here 4 states. So here we have AB can be 0, 0, 0, 1. I'm just copying from the previous slide. So we have these 4 states. You can see them here, 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 and here, right? So this is actually is AB. So what is shown inside the state here is AB. This is the present state. Okay, this is AB. This is AB, right? So we have 4 states. The arcs indicate the input X. So this is X here. This is X equal to 0. This is X equal to 1. So when X equal to 0 and we are in state 0, 0, then the next state will be 0, 0. So basically we have a transition from 0, 0 back to itself when X equal to 0. When X is equal to 1, you have a transition from state 0, 0 to state 0, 1. Let me just clean up this. So that's here state 0, 1. Okay, so you have this transition here, okay, from 0, 0 to state 0, 1. That's when X is equal to 1. If you are in state 0, 1 and the input X equal to 0, this will take you back to state 0, 1. You can see that here you have a transition from the state back to itself. That's when X equal to 0. And when X equal to 1, you go from 0, 1 to 1, 0. So therefore here you can see that we have this transition. Okay, from 0, 1 to 1, 0, that's when X is equal to 1. So that's X equal to 1. This is the X that appears, the input that appears on the arc, and so on. Now notice that the output Y depends on the present state only. Now I'm showing here the output Y inside the state. So let me clean up this again. Notice that the output Y appears here. That's my output Y. This is here the output Y. So I'm showing here AB slash Y inside the state. I'm showing the output inside the state because the output depends only on the state and does not depend on the input X. So in this type of sequential circuit, the output does not depend on the input X. So we can show the output inside the state. So notice that here when the state equal to 0, 0, the output is 0. When it is 0, 1, the output is 0. It does not depend on X. It does not depend on X here. Same. Here, when 1, 1, you get the output equal to 1. So notice that only when the state is 1, 1, you get the output equal to 1. If it is 0, 0, you get 0. 0, 1, you get 0. 1, 0, you get 0. Only 1, 1, you get 1. Okay, so you can see that here we can easily draw the state diagram from the state table. That's actually so simple and so easy. Once you have practiced this, this will become very easy. So the analysis of sequential circuits is really simple. It's not really that difficult. All you need to practice. There are many exercises that appear at the end of the chapter in your textbook. You can actually solve, you can practice. This is important. There are also many questions in the previous exams that you can also practice. طيب, any question about this example? Do you understand this fully? I do have here another example about a sequential circuit with a JK flip-flops, but I'm going to skip a JK. We can do the analysis the same way that we did in the case of D-type and the T flip-flops. But JK, the equations are slightly more complex. So for this reason, I'm going to skip them. I'm not going to give you any question about JK in the quiz or in the final exam. So you can actually study this material. It's interesting, but I'm going to skip it. Okay. So notice that we can look at the J and K input equation. So we can obtain here the equation for JA and for K. The same thing here for B. JB and KB. And based on these equations, we can write the next state equations. We can substitute, and we can actually get equation for the next state equations for A at t+1 and B at t+1. So we can do that, and we can draw, okay, the state table based on these equations, and we can draw the state diagram. That's basically it.